So this is the second video for numbers 11 through 15 of the paper twos of the A5 Galilean and what was the it's relativity, special relativity. I'm sorry. I had to think of the word special relativity equations. So the first, number 11, says spaceship travels from Earth to the orbit of Mars at a constant velocity of 0.4 c. So the distance traveled by the spaceship is 2 times 10 to the 8 kilometers as determined by an observer on Earth. That would be in reference frame S. And then the spaceship is going to be S prime. And calculate in kilometers the distance traveled as measured by an observer in the spaceship. Okay, so the mark scheme gives it to us, but I kind of wrote it out a little bit more expanded. We have that the contracted length is the proper length over gamma, where gamma is 1 over radical 1 minus v squared over c squared. We know the spaceship, the S prime speed, is 0.4 c, and so they work out the gamma Lorentz factor as 1.09. So therefore, the contracted length is the proper length of 2 times 10 to the 8 kilometers divided by gamma, giving us a contracted length of 1.8 times 10 to the 8 kilometers. Okay, so 11b. Well, the spaceship is traveling, a radio signal is sent from Earth to the spaceship when it is 3 times 10 to the 6 kilometers as measured from Earth. All right, so as measured from Earth, that's important. All right, so distance is 3 times 10 to the 9 meters, because we have to, this is kilometers. So if we're going to be dealing with meters per second in the speed of light in meters per second, we got to convert back to meters. Then it says, show that, according to an Earth observer, the time taken for the signal to reach a spaceship is about 17 seconds. Well, we know that light travels at constant speed, and constant speed is v is s over t, but we're speaking specifically about light, so we're going to get rid of v and then just say c. And I want to avoid confusion. In the mark scheme, they use d instead of s, so we'll use d. And so the distance to an object that you shine a light beam at is the speed of light times the time, and we're looking for the time here. But we need to acknowledge that the spaceship is also in motion, right? So, and it's moving at a significant portion of the speed of light. So the distance that the light beam is going to travel is, here, there's a light beam. Let's make it red like a laser. Right? So then the light goes to the spaceship, but the spaceship is also traveling. So yeah, the spaceship is moving with a velocity v, so we have to account for that as well. And so the distance to the spaceship is the light travel distance, but also the vt of the spaceship. And so we know the speed of light, we know the distance that the Earth observer saw the spaceship at, 3 times 10 to the 9 meters. But while the light is traveling, like in that time that the light is traveling, the spaceship also moves a little bit, so we need to account for that. And we know that the spaceship speed is 0.4 the speed of light, and so let's go with that. The only thing we don't know is the time. And so the mark scheme kind of already did the math for us on this. So t is d over c minus v. And so we wind up that the time is 3 times 10 to the 9 meters. And then throw in some units. And then 3 times 10 to the 9 meters. And then the bottom, the denominator is 0.6 times the speed of light. That gives us a time of. And so yeah, in the end, there's our 17 seconds that we get. But then the spaceship sees the proper time. The Earth sees the dilated time, and so the spaceship's going to see less than 17 seconds, but how do we know that? We have an equation for that. And so here's our equation right off the data booklet. T prime is gamma time minus Vx over c squared, and so the V is 0.4 c, but then x, where does the c times 16.7 come from? And then keeping in mind that we can represent x as ct, and so we know what t is. It's this 17 seconds. They're using the 16.7 as the actual answer. So that's where they're getting the 0.4 c is the velocity, 16.7 c is how far, and then over c squared, so then the c's all cancel, ding, ding, ding. And so we have 1.09, which is gamma. We figured that out before. That's gamma, times the dilated time of 16.7 minus 0.4 times 16.7, and that gets us 11 seconds. And speaking of 11, that's the end of number 11. Let's take a look at number 12. We have a Minkowski space diagram with two different reference frames, S and S prime, graphed. And we have four different events that are plotted on the diagram, A, B, C, and D. And it says the CT and x-axis are drawn for observer P, so observer P would be in the frame S, and then observer Q is moving with respect to P, so that's going to be in S prime. And then so we have the CT prime axis drawn for that observer Q, and then the light line is also drawn. The world line for a photon is drawn. And it says the scale on both axes is the same. That's interesting. That's usually not the case. But okay. Yeah, when I say both axes, yeah, that's usually not the case. So that's weird. Anyway, what's the speed of observer Q with respect to observer P? So for that, we know that tangent of theta is the speed of the moving reference frame over C, and theta is the angle between the S axis and S prime axis, or angle between CT and CT prime. Let's see. And so I used a protractor and I measured that angle to be 31 degrees. And so tangent of 31 is 0.6, and so the speed of S prime is 0.6 c, which agrees with the mark scheme. Looking at the mark scheme, it kind of does make sense that it says use of inverse of the gradient of the CT axis, CT prime axis. Gradient would be CT over X, so the inverse gradient would be XC over T, which if you look at how, in terms of like the rise over run, there are, rise over run is 10 over 6, so run over rise would be 6 over 10. You do get 0.6 c. I don't think that solution is as intuitive as just using the equation on the data booklet, tan theta is v over c. Like, I don't know why they didn't use that. It's right off the data booklet. Anyway, they will give credit for this. That is the way you should solve it, and you do get 0.6 c. And then it says draw and label the x prime axis for observer Q. And it says draw an axis x prime through B and D. That will work, but really the solution. And so x prime should be the same angle from x as CT prime is from CT. 31 degrees. If I do that, that line should pass through B and D. So I used a protractor to mark 31 degrees. And then if I draw that line, and sure enough, that line at 31 degrees from the x-axis connects both B and D. All right, now for B. 12b says, list the events that occur simultaneously according to observer P, which is in frame S. Simultaneous would be same time. Let's look at the graph. So we're looking at the X and CT axes. So A and D would need to be on the same line on the CT axis to be the same, to happen simultaneously at the same time according to frame S. There it is, same time, A and D. But that's according to S, not S prime. Or in other words, it's according to observer P, not observer Q. So A and D. Now, according to the events that are shown, we have to see which one occurs first according to Q. Let's look at the diagram. So to show when events happen according to Q, which is using the CT prime axis, we're going to draw lines that are parallel to the X prime axis to see when the events actually strike this CT prime axis. And so we're looking at, I can see that C is the earliest, going down into the negative CT prime, kind of like representing before things that happened. And I can see that A happens last. So here's the line for A. That's a pretty terrible line, but close enough. And so in terms of intercept on the CT prime axis, I have C first, then B and D, and then A is later. So which happened first according to Q in inertial reference frame C prime? That would be C, point C. Okay, now let's look at D. It says, explain using the diagram why light from events A and D is received simultaneously by observer Q. So it's specifically talking about light emitted from events A and D. And so light, so the world line for a photon for light is 45 degrees. We can actually see that in our diagram over here where the light line is given to us, and yes, it is 45 degrees. And so basically we would need to see light lines emitted from A and D at 45 degrees that intercept the CT axis. So let's take a look. You can't emit light back in time, but you can emit light forward in time. So this could be a light line for D, except, like I just said, you can't emit light back in time, so I'm erasing the line that goes back in time. So that's 45 degrees, that's a 45-degree angle, but I do not see that intercepting the CT prime axis. However, I can also, there's 90 degrees to that, and there we go, that light beam does intercept the CT prime axis. Let's take a look. Let's do the same thing with A. And again, the reason why these are 45-degree angles relative to frame S prime, to relative frame to frame S, is because just like the light line is 45, that is the maximum slope, or I should say the minimum slope can't go any lower than that because that would imply something faster than light. And so 45 degrees is the speed of light. And so those are my 45-degree rays from D. Yes, they're at right angles to each other. I'm talking about that the lines themselves are at 45 degrees relative to the ramp. To the graph. What am I talking about? To the graph. And so here for A, I have a line 45 degrees going this way, roughly 45, and that's not going to intercept the CT axis. But if I go the other way, lo and behold, ding, yes, they do meet at the same time, at the same point on the CT prime axis. So these are not the beams that I want. I'm going to get rid of these. Boop and boop. But they're showing that. So that's why the mark scheme says it shows 45-degree lines from A and D that meet on the CT prime axis. There they are. Right there. Okay. And that's the end of number 12. Let's move on to number 13. Muon question. And actually, this one, number 13, was kind of formatted sort of weird, and there's really only one question that's really relevant to relativity. So I'm going to redact all of the stuff that is not relevant. This is a repeat, and so the mark scheme that goes with it. This we don't need. Additional magnetic force because the muons are in motion. That's an SL thing. Which force is greater magnitude? Net force must be repulsive, but it's not a relativity thing. But so here we are, B. And we have an example where the mark scheme pretty much gives the answer, explains the answer pretty well. So, and I'm sorry, one other thing is the net force must be repulsive. Why is the force repulsive? Because it says so in the problem. There's a repulsive force. Um, and then, okay. But anyway, B, in muon decay experiments, muons produced high in the Earth's atmosphere move towards the ground at speeds close to the speed of light. Detectors on the ground record the arrival of the muons. How do these experiments provide support for time dilation? All right, so there's a couple of points here. So you should know, first of all, that muons have a short lifetime because they decay into electrons, but they have a short lifetime. So if they have a short lifetime, without relativity, few muons would reach the ground. They would just decay into electrons in the atmosphere. But it says experiments show the arrival of more muons than expected. So we're getting more muons than anticipated. So the lifetime has been increased. So how could the lifetime have been increased? Because of time dilation. So this is one of the last things we're going to talk about in the relativity topic, but the muon experiments are testable, so here's an example of that. Here's number 14. So 14 is an interesting question. It says there are two clocks and they're a distance d apart and they've been synchronized. A is at the origin and B is some distance away in the same inertial reference frame. It says suggest a way by which the clocks were synchronized. And so I was thinking, it's like, well, the way you would synchronize a clock is that you set them to the same time and move one, but at a very slow speed, so that there are no relativistic effects or negligible relativistic effects. And actually, that is one of the choices. I mentioned that in class, but that's one of the things you can do. And then you have where it says alternative 2, both clocks are set to read 0, and then a light signal starts from the center between them, and then it hits them at the same time, and they start them at the same time. That's a good way of doing it. But I kind of like the first option. It says clock at a distance d from the origin is set ahead equal to d over c. So following that, speed of light is d over t, so t is d over c, and if you set one of the clocks ahead by that amount of time, and then shine a light beam from one clock to the other, that accounts for that travel time, and then they're at the same time. I find that, I kind of think that's the most complicated, but I also think it's the most creative of the solutions, but any one of those would be fine. And the last question here is number 15 with multiple parts to it. So we have a spacecraft leaving Earth with a speed of 0.8 c relative to Earth on its way to a planet 12 light years away from Earth. And it says, according to Earth, which is at rest, find the time of arrival. So we could just use regular old v equals d over t, assuming a constant speed, or s over t. And so t would be s over v, so 12 light years over 0.8 c is 15 years. Now I just wanted to comment on the units. So it's kind of like, how does light years over c give me years? And so in light years, the word light is actually making reference to the speed of light. And how do I know that? So we know that light years measures distance, does not measure time. And we know that as v is s over t, then s is v times t. Well, t right here is going to be years, and light years measures distance. And so the word light must be measuring the light speed. It really should say light speed years, I guess, but that's where light years comes in. So yeah, light years over c gives time, gives years. Okay, so that's 15 years, but the spacecraft is going to see that as a dilated time, and then the spacecraft is going to see t naught or t prime, that is the proper time. And so to figure out proper time, so yeah, 12 years is, 15 years is, wait a minute, why did I write 12 years? Oh, it's 12 light years. Duh. Yeah, 15 years is the time, so this should not read 12. This should read 15. 15. But that still gives us a proper time of 9 years as viewed from the spacecraft. And so now we have the spacecraft is passing a cargo ship. The spacecraft is going 0.8 c. The cargo ship is going 0.6 c. And it says the proper length of the cargo ship is 992 meters. It's a weird number. And the speed is 0.6 c relative to Earth. And it says BI. What is meant by proper length? Mark scheme says length of an object in an object's rest frame. In other words, and that probably is the best answer because that's proper length of any object is the length of the object in the object's rest frame. But in this instance, it'd be the length of the cargo ship as measured by the cargo ship. Because even though the cargo ship is in motion, the cargo ship, like looking at itself, it is at rest. So the people inside the cargo ship are at rest relative to the ship. So they would be measuring that 992 meters inside the cargo ship. But the spacecraft would see a different length of the cargo ship. BII says, show that the speed of the cargo ship relative to the spacecraft is 0.946 c. So yeah, this is a relative velocity formula. And the formula in the data booklet is u prime is u minus v over 1 minus uv c squared. You can also rewrite it as, from the other perspective, as u equals u prime plus v over 1 plus u prime v over c squared. So we put in our values. Of course, the cargo ship's going the other direction, so we're going to give it a negative velocity. All right, I forget what I said or didn't say, so I'll just say it all again. U prime being the speed of the cargo ship relative to the spacecraft if spacecraft is u. So u is 0.8 c minus negative 0.6 c for the cargo ship. And so I throw it all together, I get negative 1.4 over 1 plus, because you're multiplying a negative times a negative, 1 plus 0.48, because 0.8 times 0.6 is 0.48. So 1.4 divided by 1.48 gets me 0.946 c, which agrees with the mark scheme. So length of the cargo ship, according to the spacecraft, the proper length is 992 meters, but the spacecraft will see the contracted length. First, you got to figure out what gamma is. Well, now we know the speed is 0.946 c. Throw that in for v, and you get a gamma of 3.08, which is pretty high. And then the contracted length is the proper length divided by gamma, and so we get 322 meters. And now we have a Minkowski diagram, and says spacecraft approaches the cargo ship. Light signal is emitted from the front of the cargo ship towards the back. From front to back. Situation is represented in space diagrams that shows the rest frame of the cargo ship, and F and B represent the front and back of the cargo ship. When light signal is emitted, the scale on the axes is the same, so there's the blank diagram. Of course, they put the question over here, right? There's no question over here. It says C. That's the setup. Is there a CI? Yes. Annotate the space-time diagram to show the arrival of the light signal at the back of the cargo ship. From front to back, label this event using the letter A. So it's going to come from F and go to B, but we can't draw it straight across like that because that would be literally instantaneous. We have to have a light line of 45 degrees. And so there's that light line of 45 degrees, and then it hits point B, and it's going to intercept on the CT axis right here. And then it wants to know what is the time that the signal takes to arrive at the back of the cargo ship according to the spacecraft. And so the formula that they're using here is T prime is equal to gamma times the time minus Vx over c squared. So we know what gamma is. And then if V is d over t, or c is s over t, so their t is s over c, the proper length over the speed of light, so it'd be 922 meters over c, plus sorry, that would be the contracted length, the 922 meters. The 992 meters is the proper length, and that's going in here for x. And then there's the c squared. So this c goes away, this squared goes away. There we go, giving us 1.91 times 10 to the negative 5. Why did I get a different answer than the mark scheme? Let's check this out. And yeah, I still get 1.91 times 10 to the negative 5. And I'm using the same numbers as in the mark scheme. I wonder if they are wrong, or if I made a mistake somewhere. Well, the setup is correct. And so that is the time, the signal, it takes the signal to arrive at the back of the cargo ship. So there we go. That is the last part of question, what question are we even on? 15? Yeah. And that is the end of the second video. And I got it under 30 minutes. Go me. All right, thanks. Bye.